Okay, so welcome guys. So because in the next videos or next very videos, I want to talk about the reduction technique to prove some problems are NP complete. So in order to prove it's NP complete, we need to basically understand some basic property of the reduction, polynomial time reduction. So it's like the ground, the ground truth you need to remember, and the definition. Okay, so definition that's if you have a language and B and a P, I write A as less or equal to B, and this P subscript, this is called polynomial time reduction. That means that for all input x, there's a polynomial reduction R runs in a poly x time, such that x belongs to the A, if and only if R of x belongs to B. So it's like you can change the input of x into the input of input of B. Okay, so that means that if one can solve B efficiently, then one can solve A efficiently. Okay, but because like each problem in A, then you can use the polynomial time reduction to make it into input of B. So if you can solve B easily, then definitely you can solve A easy. Okay, so in order to show this is true, we need to show that if R of x belongs to B, then x belongs to A. If R of x do not belong to B, then x do not belong to A. Okay. So we will see many more difficult examples or tricky examples of how to do a reduction, but in this case, that we prove some stupid example. Okay. So this is very a little bit non-trivial. So 3 colorable means that somebody give you a group, somebody will give you a graph G. Okay, so yeah, graph G, and the G is 3 colorable. That means that for each vertices you can choose a color, like red, green, or blue, and you can only use 3 colors. And on each, and the edge, the two sides of each edge cannot have the same color. Okay. So 4 colorable is that G is 4 colorable means that you can use 4 color. And these two are basically known as NP complete problems. So basically, if somebody gives you a graph and if you say that the G is 3 colorable, then just output 1. If it's 3, it's not, just output 0. And this type of decision problem is NP complete. And but in this video, we will show that 3 colorable polynomial reduction to 4 colorable. Okay, so that means for each we need to find R, right? So it's like for each graph, right? For each graph, 3 colorable graph or what? For each graph, we need to find another graph. Let's say G prime, and such that it has this property. Okay. It's very amazing that this is somehow trivial, right? So if someone give you a graph G, and then you get an additional node that's called H, and then you connect each edge, each vertices in G to H, right? Connect all of this. Okay, so it's obviously that if the right hand side is 4 colorable, that means you can use 4 color, right? But H connected all points, so H must be a unique color, like white, which is different from red, green, blue. So if this graph is 4 colorable, then definitely G is 3 colorable, right? Because you can remove H. And if this graph if this guy, right? If this guy is 3 colorable, then definitely this is 4 colorable, right? You just add any H. So it's easy to prove that it satisfies this property. Basically, I already proved. Okay. So the 3 properties I want to show this is very important. It's these 3. It's very trivial, but you will need this. And basically, people do not write them down. Okay, so people just assume that because somehow it's trivial. Okay, the theorem 1 is that if A polynomial reduction to B, and B is a polynomial time, B can be solved by polynomial Turing machine, then A belongs to B. The reason is that there is this Turing reduction, right? Polynomial reduction R, and a polynomial Turing machine and B such that when we know x belongs to A, right? And we know that this is polynomial Turing machine, so MB can run R of x. So MB runs R of x runs in polynomial R of x time, right? But R of x is also polynomial, so runs in polynomial x. So it means any x belongs to A, you can create a Turing machine which composites with this R. So you can view this composition with this R as another Turing machine. And it definitely runs in poly x time, right? Because the composition of polynomial are polynomial. Okay, theorem 2, if A is a polynomial reduction to B, B is polynomial time reduction to C, then A is polynomial reduction to C. And this is called transitively. It's also trivial. because we have two polynomial reduction, so R2 composite value R1x belongs to C, right? Because from definition, composition of polynomials are polynomials. Okay, and theorem 3 is very important. That basically, if you want to prove somebody is NP complete, someone is NP complete, you use this lemma. Okay, so if A is polynomial reduction to B and A belongs to NP complete problem, so this means that somehow you already find some question which is difficult and NP complete problem, but you know B is also NP, right? So and your intuition will tell you that B is NP complete. Okay, and the proof is if A is NP complete, that means for every NP, right? Every 1P, Y can be has a polynomial reduction to A. Okay, but by definition, A can be polynomial reduction to B, right? So from these two, we get the Y is polynomial reduction to B. So every NP complete NP problem can be polynomial kind of reduction to B, and also B is NP, so B is NP complete. Okay, so theorem 1, theorem 2, and theorem 3 are very important in the algorithm, in the complexity theory of algorithm, and then we will use these to prove various problem NP complete. So this is the reductions diagram, probably the most important technique in the complexity theory. Okay, now I will see you guys in the next video, and be sure to subscribe to my channel. Thanks.